Arcs and sectors. This is, of course, what we call a circle. Okay, that's a circle. We know the circumference of a circle, 2 pi r. We know the area of a circle is pi r squared. But what if I'm interested in not the complete circle, but just a piece of it, an arc of the circle, or a sector of the circle? So the AB, the piece of the circumference, is an arc. And in fact, there's actually 2 arcs there. The little bit we call the minor arc, and then the other big bit is the major arc. So it makes 2 arcs. If we wanted to find the length of just that piece, we're basically saying, well, what proportion of the circle do we have? Because we're using radians, it works quite nicely, because the complete circle is 2 pi radians. And our angle theta, what proportion is it? Well, we've got theta out of the 2 pi. So if we multiply that fraction, the 2 pi that's in our circumference formula cancels, and we get a lovely neat formula. The length is just simply going to be the radius times the angle. But it's important that the angle is in radians for it to work, because that's what got the pi's to cancel and all that. So the length equals the radius times the angle. Okay, well, let's do a similar thing for the area of our sector, the piece of the pie. Again, there are actually 2 sectors there. The minor sector is the piece of the pie. The major sector is, I guess if you're greedy, the big bit. So again, we could do the same thing. We're saying what proportion of the circle do we have? So we'll multiply it by theta on 2 pi. Again, the pi's nicely cancel, and we get this neat little formula, a half r squared theta. And once again, theta needs to be in radians for it to work. Okay, well, let's just do a quick little example. Here's our circle. The angle is 45 degrees, the radius is 5. Now, I deliberately put it in degrees to remind us we got to have it in radians. So if they do mention degrees, remember to convert it to radians. So the length of the arc AB, radius times the angle is pi on 4 radians. So there's our exact value, 5 pi on 4 centimeters. If we wanted to approximate that, then 5 times 3.1415, etc., 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 divided by 4. That'll get us the length of the arc. The area, half r squared theta, let's plug into that formula. Again, an exact value, 25 pi on 8 centimeters squared. But what if we just wanted to find not the sector, but the segment? So the segment is when you draw the chord in. So I've drawn the chord AB, and it's that piece that goes to the circumference. So again, there's actually 2 segments there, the minor segment being the smaller one, the major segment being the large one. So some people like to create a formula, because when they say, well, it's got to be the area of the sector, half r squared theta, minus the area of the triangle. Now, our triangle here, we can use that sine rule for the area, half AB sine theta. Well, in this case, A and B would be the same because they're both 5 centimeters, they're both the radius. So we get a half r squared sine of the angle and combine it into one formula. Some people like to remember that formula and just use that. Personally, I just always go, oh, well, I know it's the area of the sector minus the area of the triangle. I don't worry about the formula. But when we sub in, well, I've written it as an exact value. The area is 25 pi times the square root of 2 minus 100 all over 8 root 2 centimeters squared, and we're happy. So 11i is playing around with that, trying to find areas and lengths of sectors and ideas.